All right, trying. Uh-oh. Hang on. Sorry. I was just trying to get the stream going. Okay, might be okay now. Perfect. All right. So now we're ready to look at kind of I call it our second tour of the periodic table. And so let's start. So we're kind of going to look at the periodic table again. And so we can pull up our P table. So P table is really useful. And so we can look at our electrons, but let's kind of back up for a second here. And so I don't know if you guys like maybe in school or something before, usually you're given kind of this oversimplified onion model of the atom that you might be familiar with. And so we can kind of look at our structure here. And so we have right in the center of our atom, our nucleus, of course. Oops, sorry, I totally botched. Nucleus. And so like we kind of mentioned on Monday, so our nucleus contains our protons and neutrons. And again, right, they make up our main mass. So that's our center. And so now we want to look at the electrons, though, because the electrons is where all the action happens. And right, depending on your number of electrons, and we're going to see, right, the patterns. So we're going to kind of go back to our tour of the periodic table and go through again and kind of see, oh yeah, that's why that reacts in that manner. But let's look at kind of our first overview. And so we have this like oversimplified onion model that you may have seen before, again, in your past, or maybe, you just kind of heard this in passing. And then usually they go like 2, 8, 18, and 36. That corresponds to the number of electrons. And so now we want to like dive into what this really means and get a better sense of this. And so I don't want to like go too deep into atomic orbital theory, but we still want to have like a little bit of taste of what's going on. And so all these things come from solving the Schrödinger equation ultimately, right? And so again, this is just giving a little background. So okay, basically we have our Schrödinger equation, and then we're trying to map out our probability density. And so this is where everything comes from. And so we start off with, and then we can have, our first energy level. And sometimes called n equals 1. And so that's this little part right here. And so let's see what that corresponds to. And so first of all, we have our s orbital. So that's our first orbital. And so let me see if I have my periodic table, because we might want to annotate some stuff. Sorry, I was trying to grab a periodic table from somewhere. There we go. Let me steal this one and put it in our notes. All right. So we have our first energy level. And so we might want to write that. So we can annotate. So I might annotate it in this way. So first we have, so this is our S block over here. We'll get into that. And then helium should of course also be in that S block. So P table kind of shows that a little bit better. So if you go to this electron configuration, and so there's your S block. And again, we're just saying that our s orbital looks like a sphere. And so the other important thing about our s orbital is they can only hold 2 electrons. And so that's kind of implied by our little block. So if we go back to our block here, and we see, okay, it's only 2 wide. And so that corresponds, again, to the 2 electrons that fill in there. And so let's just start at the top, because we do want to learn electron configuration with this. So we can start with hydrogen. And then again, looking at our periodic table. And so I might like have one that you can annotate. I can make some more copies if I don't have some floating. So this is our first row here. So there's n equals 1. And then S block. So our electron configuration, and again, we should just have 1 electron for neutral hydrogen. So that's going to be 1s1. And again, this is for neutral, and so we have 1 proton and hydrogen, so I expect there, right, to be 1 electron, again, for neutral hydrogen as shown. And then we can keep going, right, across the periodic table here. And so now, so 1, 2, so next element over is helium. And so now this explains why it's kind of over here, and why it's part of the noble gases, but it's really only why it only has 2 electrons. So helium, right, is now 1s2. But now we say that this is satisfied by the duet rule. And basically we're saying for our first orbital that this is a complete shell, right? So later we're going to talk about the octet rule, but again, helium technically violates it because it only has the s orbital, right? So this means that it is completely filled with our s. Does that make sense? And again, just ask questions. Oh. Satisfied by the duet rule. So duet, right, meaning 2. So again, all we're saying is that we have filled up our s orbital. And then other ways to show this is sometimes you see like these symbols, so people will draw a line, and we can label this 1s, so this signifies our orbital. And then we can fill it up with 2 electrons. And so electrons are drawn by this half arrow. So that's our electron. And so the other thing is that we can't have an electron occupying the same space. So that's why I wrote 1 up and 1 down to show that they're in different positions. So sometimes this could be labeled as like +1/2, -1/2 if we're going to quantum numbers, but we don't quite need to go there in this class. Yeah. So they're just, yeah, so it's the first one, and we'll kind of get to it, but it's our lowest orbital, right? And then it's a sphere, so that's the other thing that's important. And then ultimately, again, where it came from is from solving the Schrodinger equation. So this is really a probability density map, because, right, we can't know exactly where the electron is. So the electron is somewhere spinning in this cloud, and we can look at our probability density map and say, okay, well, it's probably in this region at some point in time. And so it's likely to be found in the sphere, but we can't say exactly where in its path it is. All right, so that's just our first energy level. So now we can go down to our second row and start that. And so, right, this is still our S block. And so let's just go in order. So lithium now. So lithium. And so it's proper electron configuration. So 1s2. And again, you just fill it in across, right? So you just go across the periodic table, fill it in order. So, and that's kind of what I'm doing right now, right? So again, we have 1s1, 1s2. And this is also saying, like, we have to start at the lowest energy level, right? So to get to 3 electrons, you always start, so filling in the 1s, and then the next one is our 2s. And again, it goes just in order. You have this to kind of help you. I know people have all sorts of charts and tricks from like Gen Chem right? And like maybe you've seen that with the lines and stuff. But I find that if you just go in order of the periodic table, that's kind of the most clear here. And so then we start lithium. And so that leaves us with 2s1 here. And so now we can start to see the reactivity, right? So we have, and if we go back to our other notes, right, now we're starting to connect the pieces. So again, group 1. So now we're back at our electrons, right? So 2s1. And so now it's implying, okay, well, that's why it has 1 electron to lose. Let's go back to this. So again, this is considered our valence electron. So when it does a reaction, right, this is where it's going to be losing that electron from. And so that's telling you, yes, that's how it's going to end up in the 1+ oxidation state, right? So we can kind of write that out as an aside. So then lithium 1+, its electron configuration is 1s2 there. Because again, it just lost that valence electron. And then we can already imagine, well, this is why it's really not going to lose any others, because now this is a stable duet configuration, right? Or we could kind of call it like noble gas, but I'm just using duet since we only, again, filled in our 1s2 there. So it's just like helium. And so then we can just keep going across the periodic table. And maybe you even want to put, so this is NS1 is what the pattern's going to be, right? All these are always going to have 1 valence electron. But like I said, we'll keep getting there. So let's go the next one over. So now this is going to be 2s2 for the ending, but let's write out the full electron configuration. So beryllium, 1s2, 2s2. And so something that you want to do is just double check that you have the correct number of electrons. Obviously, it's kind of easy right now, but once we get down to like lead or cadmium, or heavier elements, europium, then we want to double check that we have the correct number of electrons. So again, we're looking at beryllium. So beryllium, right, atomic number 4 here, zooming in, so 4 protons. We're doing neutral beryllium, so we should have 4 electrons. So 1, 2, 3, 4, right? So everything looks good. And again, we're seeing, okay, these are the valence electrons. So again, all the action is happening from there. So when it makes a compound, these are the 2 electrons that are going to leave. That's going to give us, right, beryllium 2+ with, again, that 1s2 electron configuration, just like helium again. And so, right, we're slowly starting to see a pattern that, okay, that our other elements that aren't noble gases, they want to be in the noble gas configuration. So again, that's why we find that these have a tendency to react in the way that they do. And so let's keep continuing. All right, so now we start something a little new. So now we start our P block over here. So now let's look at our P block so we can kind of see it. So it's all these things over here. I'll highlight it. So that's our P block. I should have highlighted it in a different color. So P block. And so let's look at what that means for a second. Again, I'm not like super expecting you to know all these intimate details about the orbitals, but I still find it helpful to at least kind of put the pictures to what's going on. And so now we have 3 types of p orbitals, and so they just are labeled by their directions, so x, y, z. And then, so there are 3 p orbitals, and then each one of those can hold 2 electrons. And so that means, right, there's 6 electrons total in our p orbitals, right? And we can remember that. I'll let people copy that down. Don't want to go too fast. And so if we switch back to our periodic table here, so if we count it, right, our P table, so it's 1, 2, 3, 4, 5, 6 across. And so that again reminds us, okay, that means 6 to fill our p orbital. So good. So now we'll continue with that. And so we can write, again, our electron configuration. So now we have boron, so 1s2, 2s2, and then 2p1 here. And so that is something to note. So again, the first energy level does not have any p orbitals. So when we're on the second energy level and we have a p, we start with our 2 here. And so then 1s2, 2s2, 2p1. Good, so that's our electron configuration. And again, outermost electrons, so these are our valence electrons here. And so, right, we can, because you always have to start with your total number of electrons, right? So we look at boron, so it's 5, so it should have 5 electrons. And again, you always start with your 1s. It just becomes your core electrons that are there, right? But they're not really contributing to what I would call the bonding nature. So then we can see, right, that boron has 3 valence electrons. Yeah. Yeah, once we get to the second row. So I'll define that. So yeah, when I keep talking about these valence electrons, yes, they are the outermost electron. And again, they usually, I'll call it, right, dictate action or reactivity. And again, we're seeing that, right? We're seeing our pattern, albeit slowly, right? And we can continue this on to next lecture. Again, like the first lectures are always kind of either intense or like I don't want people to be lost, but we're just trying to lay the foundation. And right, everything kind of builds upon this whole valence electron concept. And so let's continue labeling. So then we have NS2, NP1 for boron. Again, they're going to keep that pattern. And not to get too much down the rabbit hole already, but this is why boron is a cool compound, because it has this weird thing of 3 valence electrons. And so it tends to just make 3 bonds actually like this in a covalent fashion. But well, we haven't gotten there yet, but this is weird because usually we expect a compound to have 8 electrons, but this only has 6 electrons on boron. And then that's strange. And then these species, though, are super reactive, right? So, like, you get so much information from just the valence electrons, because now we know, okay, well, 3 valence electrons either means it's going to lose those 3 electrons, and we typically see that in aluminum, which we'll get to. But in the case of boron, right, it's going to make this compound, and then that has further implications. So it's really, really quite cool. All right, so continuing down the line, so carbon, right, NS2, NP2. So let's write out it properly. So 1s2, 2s2, 2p2 there. Okay, perfect. And again, 4 valence electrons. This 2? The 2p2? Yeah, so it goes back to the energy levels, right? And maybe we can even go back. Sorry, trying to find where I put my onion model. So, right, the main energy levels, if we go back to this shell, so we have, right, n equals 1, n equals 2, n equals 3, n equals 4. So that's just like our main quantum shell. And then so if we go back and kind of look at what this is saying, well, yeah, yeah, because the first one, like we said, only has the S in there. But now the second energy level now has S and P. So yeah, when we went and we first started our P, and maybe let's go to. So then, right, this is, well, 6 in a compound, but it only has 3 valence electrons, right? So remember, we can look at this for 3, but it has, so again, we're just filling along down the line. So we had 2s1, 2s2, and then this started our P block, but we're still on the second row, right? And maybe you want to annotate this as like 2P to help you remember. But now, so this is 2P1, and then 2P2, and then continuing, right, 2P3. And so while we're looking at this, I actually want to start looking at a bit of electron configuration as well. And so let's kind of go back to some of these. And so looking now at electron configuration and Lewis dot structures. So I know I'm kind of like jumping ahead, but I like talking about Lewis dot structures because I want you to think about your compound in a way that's actually useful. And so let's look at this. And so if we look at our first row, right, again, we said that they have 1 valence electron. So if we look at hydrogen, and we want to be able to write this essentially as our Lewis dot structure. And so if we look at our Lewis dot structure, again, we want it to match. So the way that I want you guys to think about this, and let's look at a general structure, right? We can draw our atom here, and we have 4 sides, right? So conveniently, the way I would like you to think about it, and this might be different than what you learned at school, but we have a side for our S, and then we have 3 P's. Okay? And so now we would just want to fill it into match, but it doesn't really matter which side you call an S or which side you call a P, right? And so for going back to our hydrogen here, so hydrogen is going to look like so, right, with 1 little dot there, again just showing our valence electron. And then for helium, the way that I would like you to do it would be to write it like so, right? Because we want to show that they're in the same orbital. And so if you look at other textbooks or resources, what you may find is sometimes they may write it like this because they're trying to like distribute it, but that's not really accurate or meaningful to me, right? You're just kind of writing some dots down, but really it's not showing how it's filling up. So I don't really like that, so I wouldn't fill it like so. And then if we're looking at lithium, right, so we have lithium here. So now, again, we only care about the valence electrons when we're writing our Lewis dot structure. So again, it's 2s1 for our valence electrons. So that means lithium, right, will just have a dot as well. And again, that's really showing the reactivity. Yeah. Well, well, it's in the s orbital, right? So it's in the 2s1 orbital. Yeah. So right, because you're just again like filling up, and this is where the P table kind of good graphics. So if we look at trying to show our energy levels, this is what I'm looking for. So we have, right, if we click on hydrogen, oh, my camera's covering it up on the stream. So if we click on hydrogen, right, it just shows a little ball there. So again, that's just showing its orbitals. So okay, we just have a single ball there. Helium, same thing, right? We're just filling up that one S. And then if we click on lithium, I know it's kind of hard to see, but what it's trying to show you, and you might have to just see it on like your own computer. I don't know why I can't like zoom in, but there's a small little red circle, right? So it's saying, okay, those are your valent or your core electrons, right? Your 1s2 now in the center. And then technically there's a node, so there's like an area of no electron density, but then there's like another onion ring around it. So another sphere, right, where your 2s is now. So that's where the valence electrons of lithium live, in that 2s1 right there. And so same thing, right? You go over to beryllium, okay, filling up the 2s2 there now, and then boron, now it's showing, right, your p orbitals, that it's going to look like this dumbbell shape that your electrons go in. And so the other thing about p table, like as you're learning, notice that it writes the electron configuration for you. So that's really helpful, right, to check it so you can do it. And then, okay, let me double check it with p table and make sure that I understand what's going on. And again, it tells you the order to fill it in. And so then going back to beryllium. So again, 2s2, so I would want you to write it on this side, right, showing that those valence electrons are still in one orbital. And then once we get to boron, again, same thing, right? We want to write our Lewis dot structure kind of reflective of that. So I would write boron, 2 electrons in 1, and then 1 on the side there. Now this does bring up kind of other issues and discrepancies. And so for boron, I just showed you that it makes 3 bonds, and so it does tend to do like this weird hybridization. And so this would be like, okay, I'd rather that you probably write it like this just so we show, again, the electron configuration, and we'll leave kind of the oddities for bonding and so forth. And so that brings us to carbon, right? So carbon is also special. And so carbon, I would write it like this, even though I was like, don't write it like this. So carbon is kind of an exception. So carbon makes 4 bonds. I think we've said that, but we'll say it again. And so carbon always tends to have this tendency to hybridize. And so it's okay to write it like this. But then kind of jumping ahead, like for silicon, for example. And so silicon, we'll get to its electron configuration in just a second. But silicon, right, I would want you to write it 2 in the S, and then write our 2p. So then you distribute your p electrons evenly. So 1, 2, 3, 4, 5, 6. So those follow, I don't know if you're familiar with Hund's rule, the candy rule, right, where you give everyone a piece. But again, you want to fill your s orbital first before you start giving your p orbitals electrons. And so the other way to write this is, again, looking at your valence electrons, so 3s, filling those in first. Then you would have your 3p orbitals, right? So, and then you fill them up. So 1, 2, and so you put them in separate orbitals before doubling back and pairing them. And so let's jump ahead and see if we can do silicon's electron configuration. And we'll, like I said, we'll keep going through this, but we can see we're going to finish out our p block. So NP3, NP4, NP5, NP6, right, filling that up. Let's skip over. So this would start 3. So 3s1, 3s2. This is 3p over here. And so you can probably start to get a sense that this starts getting tedious, right, to write out our full electron configuration. So for silicon, that would be 1s2, 2s2, 2p6, 3s2, 3p2, right? And again, you can double check yourself. So 2 plus 2 is 4, plus 6 is 10, plus 4, so plus 2 plus 2, so that gives us 14, right? So 14 electrons. If we go back, okay, silicon is 14, so good, that matches. Okay, but this is starting to get rather tedious. And so there's a shorthand, and so the shorthand is that we can go back to the previous noble gas and then put it in bracket, and then that's our noble gas shorthand. So for silicon, right, we can go back to neon. So neon, again, is our previous noble gas, and then we just start filling up from neon, right? So neon, and then 3s2, and then 3p1, 2, right? Just like we determined. Does that make sense so far? No? Yeah. Yeah, and they have the full octet, right? So let's go back. So let's look at nitrogen now. And again, we'll keep trying to break it down for people. And again, right, you should be kind of annotating your periodic table. You want to have all these markings, like even if they don't make any sense now, like I promise that they will click eventually, right? And so now we're at nitrogen. And so we want to do its electron configuration. And so let's just start. We'll see if you can do that for a second. So try nitrogens on your own for a minute or two. Here? Oh, that was just, right, because we have to fill along the row. So we'll go back and kind of do it. But, right, if you're filling along the row, then you just count. So 2p1, 2p2, 2p6, 2p4, 2p5, 2p6, right? So yeah, let's keep filling. So try nitrogen, right? So then it's 2p, so you can count it. All right, so what do we get for nitrogen's electron configuration? Yeah. Yep. So did everybody get that? So we got that. So that's good. And I'm trying to make sure that this makes sense. So again, right, our valence electrons there, just our outermost shell. Yeah. Yeah, it's always like the outermost shell, right? But then it should also like match with this number. So that's the thing, is like everything should start kind of reinforcing. So then this has a little number of 5. So then, okay, I know that this group 5 here has 5 valence electrons, right? Because it goes back to the reactivity. And so nitrogen, right, we had said previously that nitrogen can either be in like this +5 technically, or 3 minus oxidation state, which is just implying that nitrogen wants to gain 3 electrons, right, and get to neon. And so some example, I know we're kind of like jumping, but then this is that compound that I was mentioning, right, that can form in the glove box of lithium nitride, right? And again, we're seeing, well, lithium has 1 valence electrons. So I need 3 lithiums to balance this, right? So lithium, 1 valence electron, 3 of them. So now we have 3 electrons. And then nitrogen was able to take all those 3 electrons, and then they would all be happy, right? So then we could write out our electron configurations from this. So lithium would be 1s2, right? Satisfied by the duet rule. Again, losing that 1 valence electron. And then same thing with nitrogen. Well, it had 5. And then if we give it 3 more, so now we can write our new electron configuration. So 1s2, 2s2. So 3 plus 3 is 6, so 2p6. So that gives us noble gas configuration. So again, just trying to tie the reactivity, right? So that we can say, okay, I know how many valence electrons there are, and this is the orbitals they're in, right? I can match it with my periodic table, yes. It says 5 over here. That matches. And then see if you can write the Lewis dot structure right now. So again, you want it to match like that. So take a minute or so. Yeah, the Lewis dot structure for N. So what do we get for our Lewis dot structure? You can kind of describe it. Yep. And it doesn't matter if you orient it in a different fashion. So that's perfect though. So that's exactly what we want. And again, this is already telling us so much information, or at least laying down the groundwork for so much information. So first I'll rewrite it as kind of the other form. So we have 2p there and 2s. So now we have 1, 2, 1, 2, 3. So again, just kind of showing the same information, right? So we can take this and make little dots. And so right, that's again just the whole point is like, if you look at a textbook and they show it to you like this, you want to understand what that means in electron configuration, Lewis dot, and this little orbital notation here. Does that kind of make sense to people? Those are the little half arrows, remember? So I said that these were the half arrows to indicate an electron. All right, so yeah, let's keep marching across then. So let's try oxygen. So see if you can write out the electron configuration real quick. So what do we get for our electron configuration? Double check your count. Perfect. So excellent. So we all get that. And so again, right, our P can hold 6 total, so we just keep on going. We can rewrite it like so. And again, right, showing that, okay, we put an electron in each p orbital until we had to pair them, so then we were forced to pair them, right? And again, we can write our Lewis dot structure to represent that, so try that, yeah. Yeah. So that's neon. So yeah, just kind of skipping ahead. But yeah, let's do oxygen's electron configuration. Yeah, so we'd have 6 valence electrons. And so I'll sketch it out as well. So 1, 2, 3, 4, 5, 6. So it should like all right, so good. So let's let's look at neon. So we did neon, right? So again, going across. So now 2p1, 2, 3, 4, 5, 6. And again, we can kind of appreciate why neon is, of course, our noble gas. And again, right, looking at this 8 valence electrons. No, the noble gases either have 2 or 8. The alkali metals are the ones with 1. Right, because I got the 8 here. And so the 1 should correspond with our alkali metals. And so neon, right, we can do our Lewis dot structure. And again, it's implying why our noble gases are unreactive, so they have our full electron shell. Essentially, right? So now their orbitals are filled up, right? And so this gets into other things. I mean, technically, they could do expanded octets and use their p orbitals. That being said, so neon is like too tiny to actually accommodate any compound. So like trying to find a neon compound is difficult. But like argon or xenon, those can react, but again, it's like rare, right? And again, chemists are always like trying to force things or make things happen. So again, even though they're full, right, they can be forced to make compounds. But like I said, not neon, but that's from a size argument. Yeah, so then, and again, you fill it up, and then, so yeah, so this is maybe a clear representation of, again, why it's a noble gas. So our orbitals are all filled up, so exactly, just like that. It's pretty good. Oh, excellent, I see it online. All right, where? Just have a minute or so. Okay, so I'll probably, I'll kind of annotate the periodic table, but like I said, we're going to need to come back and spend more time on it. So like we were kind of implying, so this starts our 3, right? So then this is our 3s1, 3s2. I said this is 3p, so same thing. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. This is where things get weird. So like I said, we'll have to cover this again. I'm just trying to like give you an overview. So this is 4, right? So this starts 4s1, 4s2. But then we have a little bit of a situation. So if we go back to our, where's my my little orbitals? Well, we had said that our n equals 3 orbital has an s, a p, and now would have a d, right? So that's how we get to 18 total. But if we go back, well, we haven't looked at any d's. And so this starts your 3d right here at scandium. So scandium starts 3d 1. And so that's kind of confusing, right? Because we were at 4s1, 4s2, but these energy levels are pretty close, and so that's why they get filled in this order. So it's 4s1, and then we can do our 3ds, right? And like I said, we'll go over this again on Monday, but we can just map it out. Okay, so then zinc is 3d10, and going back again, just so we can appreciate it. So there are 5 d orbitals, right? And just like before, so each orbital has 2 electrons, or can hold 2 electrons. So that gives us 10 total d electrons, which again matches with how wide it is, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that matches, so that helps you remember. And then this starts 4p1 back up. And so we'll probably stop there in the interest of time. We'll keep continuing because there's some other oddities over here, but I don't want to start it and rush it. But that at least gets you pretty far. And so right now you guys should be able to figure out up to barium, just kind of following the same pattern. So this is 4D, but like I said, I'll save this because that gets wonky, and we'll talk about that. Plus, we will also go back because there's some funny stuff up in here with our electron configuration, and we'll look at it. We'll talk about the exceptions. That being said, like, I won't necessarily like quiz you over exceptions and trivia. I'm not that type of person. But like I said, we'll talk about like accepted answers. All right, any other kind of last thoughts? Like I said, we'll keep working on this, so I don't want people to feel like overwhelmed or anything. We're going to keep working on it. We're going to kind of keep reiterating this, and then we'll go and again, just like keep piecing everything together, right? Because this is our foundation. So once we know valence electrons, that drives reactivity and the compounds, the shape, everything. So we just want to make sure we have a good foundation. So just ask questions too as well. All right, I will stop the stream and the lecture, and then I'll hand out the paper quiz for people in here. If you guys have already taken it online or something, you can let me know, or you can use this as extra practice if you want. Otherwise, just make sure you turn it in to me so you can get credit. All right, I'll keep the stream hot for just a second or two in case there are questions.